Hi, this lesson is to introduce the practical investigation / poster. You'll recall in Step Up last year you performed a prac which was designed to calculate the heat of combustion of a fuel. So you burned a certain mass of the fuel, you measured how much it heated up a certain mass of the water and calculated the heat of combustion based on that. Now it was a pretty limited prac. So much of the heat is lost, the data is not particularly reliable. However, with data we did something with it. Your job is to design an extension of this experiment. Take one factor and change it and see what happens. So usually you would take a controlled variable and turn that into the independent variable, change it and see if that has any effect. So this will be done based on second-hand data. We've got data going back for a few years now on this prac. So we've tried to work out what the variables are that have got enough data to turn into a decent report, and you'll get to choose some of the data from there. It'll be a report which will have the various sections that are common to a practical report, and if need be at the end of the day we can simply paste all of these sections of a practical report into a PowerPoint poster template and it becomes a poster as per the way it's been done the last few years. Now we'll be going through it section by section on Google Classroom. So you'll be doing, well, first of all you'll do the title, which is your research question. You'll be submitting that on Google Classroom. Then when I've approved it, basically to make sure that it works, that we've got data for it, that it's something that you're going to be able to complete the task for, then you can move on and do the second section. So it's important that you don't move ahead too far, too quickly. Otherwise, you might have to do work again if what you've done doesn't really, isn't likely to produce a viable report. It's criteria marked. You've got the rubric as one of the attachments. Have a look at that, and there are 4 criteria. Each one of them will be marked out of 5, and they'll add up to a mark out of 20, which is what you'll be awarded for this task. So you need to pay special attention to the right-hand column in that rubric. So that's the one which contains the things that you need to do to get a good mark. So for the first criterion, research question hypothesis, which is what we'll be starting off with, of course. So it has to be a question. It has to have a question mark at the end of it. And you've got to put it in the context of the sorts of material that's presented in Year 12 chemistry and the sorts of questions that are examined in Year 12 chemistry. You do that and you'll be well on your way to getting 4 or 5 for that criterion. So the hypothesis has to be a statement which makes a prediction and has to be based on the research question, of course, and has to be given the appropriate chemical context, grounded in appropriate chemical knowledge and background. You've got to have a theoretical justification for it. So go on down through that column. You need to do all of those things to get a good mark for this poster. The challenge one, the discriminating task, will be that last, the evaluation criterion, of course, and we'll get to that start of next week. It's going to run over 3 doubles, is the way I see it happening now. If these sorts of things need to change, they will change. We'll see how both the classes go, see what works, what doesn't work, and vary things if need be. if you've got any problems at any stage, just please contact me and we'll work something out. So essentially there are two types of investigations that you can do. You need to pick, well, something from one of these two types. So there's a sort of methodological investigation in which you take a factor and try and improve the way the prac ran. So essentially, we know that most of the energy is lost in between the flame and the water. So can we do something to get more of the heat absorbed by the water, get a more accurate estimation of the heat of combustion? So, excuse me, there's some of the things: using a shield, changing the distance from the top of the burner to the bottom of the beaker, changing the volume of water being heated, even changing the type of liquid being heated, having something with a different specific heat capacity. I think oil was tried one year. Type of vessel being heated: you could heat up the water in a tin as opposed to, which is more highly conductive, as opposed to a beaker. You can change the arrangement with a lid on the beaker. I can't actually recall which our control is, whether it's lid on or lid off, but that could be the factor that you change. Now the other type of investigation is one that looks more at the chemistry behind it. So take that we've calculated heat of combustion. What does that tell us about the fuel? Can we predict from the type of fuel which is going to give us a higher heat of combustion? So we can see the relationship between molar mass and heat of combustion. So especially if we're measuring heat of combustion in kilojoules per gram, do larger fuels have a higher heat of combustion in kilojoules per gram, or a lower heat of combustion in kilojoules per gram? Is the number of carbons critical in affecting the heat of combustion? Oxygens or hydrogens? Or is it the number of bonds that have to be broken? Or rather than just the number of a type of atom, is it the percentage of that particular element in the molecule that's important? And also for different fuels, you can see whether its viscosity has an effect, its boiling point. They're both values that you can research yourselves online, and we've got the heat of combustion data for a range of different fuels. You can relate that to their viscosity and their boiling point. Okay, so we start off with the title and introduction, and that means coming up with our research question. And it's that research question which is the title of your poster. So, as I've said, we're changing something. Usually taking one of the controlled variables and changing it, making it become the independent variable. So the example, we go back to the Year 11 course and colorimetry, in which we measure the concentration of a coloured solution by measuring the absorbance of light. The more light that's absorbed, the higher the concentration. Tried and tested analytical technique. Can we make it better? So a couple of simple research questions might be: is the absorbance affected by temperature? Is the absorbance affected by pH? And so they're two quite valid research questions. Now, we need to put that in the context of the course. So, Year 11 chemistry, there's a fair whack of environmental monitoring sort of stuff. So here's a context that makes sense. It's important that we get reliable data about the waste discharges of factories. However, if the pH of the wastewater varies, is that going to affect the our measurement of the copper concentrations. So your first task is to pick one of the factors that we've looked at and turn it into a question, give it a context. So I'm making up one here, you can't use this one, not sure that it would work anyway. Does the mass of the fuel burned affect the accuracy of the head of combustion? So like if we burn 2 grams of fuel compared to if we burn 3 grams of fuel, which is going to give us the better head of combustion. And I think for a lot of these methodological sorts of designs, the context that works is something like this. You need accurate data if you're going to use the data for decisions regarding choice of fuel. I think everyone who does a methodological investigation is going to have something very similar to that, my guess. So do that and submit on Google Classroom. When you've done that, you can, and I approve it, you can then move on and write your hypothesis. Now, hypothesis is a testable statement. It's something which is going to make a prediction and you are going to test that prediction. And it also has that theoretical justification. So going back to those calorimetry examples, is the absorbance affected by temperature is your question. Now you've got to make a prediction. Is it going to be affected by temperature? Or how is it going to be affected by temperature, I should say? And what we've come up with is the fact that the absorbance is going to decrease as temperature increases. And we've got a theoretical justification. It's because of the decreasing density of the solution as the temperature goes up. It doesn't have to be a particularly profound theoretical justification. It just has to be there, some basis in theory. So the pH example, I'm making the prediction that the absorbance decreases as pH decreases, and I've come up with a vaguely plausible theoretical justification. I just made it up, but who knows? It's something that could be tested. But they're the essential features. It has to have a prediction, one way or the other, has to be directional, and it has to have a justification. So it decreases because. So you will take the researcher question that has been approved already and write a hypothesis, provide a theoretical justification. That's your second posted task. And for my mass of fuel burnt, I've made a prediction that as the mass of fuel increases, the calculated heat of combustion increases, become closer to what it should be. And I'm suggesting that's because things get hotter, increasing the efficiency, reducing the amount of incomplete combustion. Who knows? I think there's a whole lot of other flaws with that investigation. A whole lot of other issues with conducting it that you would need to overcome, but yeah, it's a theoretical justification. So go away and do the hypothesis, submit it online. When it's approved, you can move on to the next task. Which is, next task is defining your variables. So remember, independent variable is the one that you change. That's the whole point of the experiment. It's what you've decided to change to see what happens. Dependent variable is the one that you measure as it responds to those changes. Control variables are all the things that have to be kept constant to stop it interfering in the investigation. So just a couple of revision questions. Why do we need all the controlled variables to be controlled? So that they don't interfere. So that any change we observe in the dependent variable, we can be confident that it's been caused by the independent variable and nothing else. And put it another way around, only one independent variable, because we've got to know that it's that variable which is responsible for the change. So variables in the colorimetry experiment. So the temperature, independent variable, one that you change is clearly temperature. Dependent variable that we're measuring is absorbance. And every other factor that you might think might interfere with stuff is a controlled variable. For the pH example, very similar. The difference is this time the dependent variable is pH and temperature becomes a controlled variable. The dependent and the other controlled variables will be pretty much the same. So the independent variable is going to be the thing that's the feature of your hypothesis. Dependent variable, what you're measuring. Now in my example of the massive fuel burnt, that's the independent variable. Dependent variable is the change in temperature which leads on to the calculation of the heat of combustion. It's kind of both. And everything else is a controlled variable. So there's a whole list of controlled variables. You're going to have slightly different list to that, but there will be a lot of similarities. So if you could go away and submit your variables list, I'll have a look at that and then you can move on to the next section. Next section is getting a materials and method. Now it's a method list that we need. We don't need an exhaustive list of materials. The method that you're given has to make the experiment reproducible. Someone else has got to be able to come along and conduct the experiment exactly as you have. Diagrams make things a whole lot easier. You've got a diagram there. You may need to adjust it slightly, but that would be a very useful starting point. And identify your variables, how they're going to be varied, how they're going to be measured, how they're going to be controlled. They're the key aspects of a procedure, a method. They're what you're going to have to make sure is clear in your method. More importantly, when you come to do exam questions on this, they're the features that you need to make sure you're covering. How you change your independent variable, how you measure your dependent variable, how and when, and how you control your controlled variables. And of course, to ensure reliability, we repeat our experiment 3 times. 3 replications is a good number. So that repetition has to be included in your method. And as I was saying, reproducibility is something which your method must be detailed enough to enable. So someone else has to become able to come along and do it exactly as you have and get, hopefully, exactly the same results. Essential tenet of the scientific method. So how would you test the hypotheses in the colorimetry experiment? So I'm just going to run through these fairly quickly. So give a little bit of detail about how we're going to change the independent variable, how we're going to measure the absorbance, how and when we're going to measure the dependent variable, and then give enough detail to ensure that variables are pretty well controlled. Repeat 3 times to ensure reliability. For the pH example, this time we've got to adjust pH. So how are we going to vary the pH? What's that process going to be to ensure it's done well? How are we going to measure the absorbance? How and when? And then similarly controlling those confounding variables. Repeat 3 times to ensure reliability. Now, you're given the basic method there. It will need to change. The diagram will need to change. So you won't get any marks just for rewriting. You'll get very poor marks just for rewriting the given the control method. It's already there in the template, so yeah, you won't be rewarded for that. And just make it clear how you're going to vary the independent variable. Make sure that it's still clear how the change in temperature is going to be measured, and if you need to emphasise how other variables are going to be controlled, include that detail. Now that's the control procedure. Like I say, you're going to change something in that, whether it's something to do with the fuel, whether it's something to do with the setup, the height, the container, the mass of water, whatever. You're going to be changing something in that. Your method has to accurately indicate that. So go away, submit that on Google Classroom. When you do that, you can move straight on and do the risk assessment, safety and environmental issues next. Probably don't need to approve your method before you do that. So safety and environmental issues is part of the method criteria. The safety issues certainly are. And environmental issues are often things that you need to consider. It's good to get a bit of practice at that. So you need to basically do a risk assessment. So I've given you some slides that can be followed, should be fairly straightforward to follow to get a risk assessment done. I've given you some SDSs for common fuels. I'm going to talk about the ethanol one when we get to it. There's also ones for propanol, butanol, pentanol. And if you've got another fuel you need to do a risk assessment for, pretty much treat it the same as pentanol. Moderately higher boiling point organic fuel, probably close enough for our purposes. So, the example that I'm going to go through to do a risk assessment is a very simple technical procedure, which is basically making a dilution of hydrochloric acid. Taking stock solution, which is concentrated 36% hydrochloric acid, and diluting it down to be, I think, 0.1 molar. So, pretty simple procedure. 500 mils of water, so half fill your 1 litre beaker. Then you measure out your concentrated hydrochloric acid. It's nasty stuff, you do it in fume hood. So you've got to do it from a beaker. So you fill the measuring cylinder from the beaker, not from the original stock bottle. You then add the acid slowly, because it's going to release a lot of heat. stirring constantly. Then you transfer your 500 mils of water with the acid into a volumetric flask, fill it up to the graduation line, mix it thoroughly, and then transfer it to the storage bottle. So it's just a fairly routine technical procedure. It does involve a fairly nasty chemical, concentrated hydrochloric acid, so risk assessment is something that needs to be thought about. So this is the risk assessment that I did. Now, first of all, we just look at the activity that you do. There are three basic phases of it. First of all is the preparation step, where you get all the glassware, probably put some water in, just get organised, ready for the critical step, which is the preparation of the dilution. So the key step to that is measuring out your concentrated acid, adding it to the 500 mils of water. Now, that's the step that involves most risks. That's the one that you're going to have to look at most closely. Then, once you've got the acid basically diluted, then you sort of finish off the dilution and put it in the storage bottle. It's probably a lower risk section. So you've got the three basic phases of the investigation. Then you look at each phase. What are the possible things that can go wrong? What are the possible hazards? So in the first one, breakage of glass. Possibly I could have included, if there's a bit of water happening there, I could have included spillage of water and the sort of trip hazard that creates. But I've just stuck with breakage of glass here. You know, it's not going to happen that often, and it's probably not going to be particularly serious if it does, but it's a hazard, especially in a crowded classroom. It's a hazard that needs to be considered. For the next step, which is the basic dilution of the acid step, measuring of the concentrated acid, that's the one that has got issues. The HCl in the stock solution is fuming. It's giving off hydrogen chloride gas. You breathe that stuff in, it's pretty nasty. You don't want to breathe that stuff in. So you breathe it in, it's corrosive to your airways. You get that stuff in your eye and you're blind. You get that stuff on your skin and you've got a really nasty burn. So three significant issues. I know when I've done something, well, this is part of our Year 12 ChemPrac in the old days. This was something I used to do a significant amount of. I was getting students to do it in the fume hood under my direct supervision, you know. Just, I was watching them every step of the way on this one. Now, once you've got the acid in 500, a little bit of acid in 500 mils of water, nowhere near as dangerous. So we've got dilute hydrochloric acid at this stage. It's not going to cause permanent blindness, but it could cause eye damage. It's not going to cause serious skin burns. It's going to be irritating. If you've got any cuts, you're going to know about it. And of course, breakage of glass is probably a hazard again at this stage. So once you've identified all the things that can go wrong, all the hazards to do with the nature of the equipment or the chemical, then you need to look at what are you doing to control this risk. Now, for the first one, if it's a classroom situation, you know, I've got you wearing PPE, so you've got lab coats on. You know, you've been doing chemistry for a year or so by now. You know how to behave in a chemistry lab. You're well trained. And I'm keeping my eye on things. If people are being silly, then I'm doing something about it. And that's a pretty straightforward one. What are we doing to control the risk on this one? Well, the corrosive to the airways. So this has to be done in the fume hood. It has to be done on the fume hood with the screen lowered and making sure that the fumes can't escape. It's also going to help prevent eye damage. You're also going to have safety glasses on, which probably should be mentioned in that, to be honest. But the screen down is also going to protect you in that case. How do we stop skin burns? Well, lab coat and safety glasses are pretty much automatic. It's probably the reason why I haven't included it here. Every time you're doing practical work in a lab, you are wearing PPE. Closed shoes, lab coat, safety glasses, hair tied back. Gloves are not automatic PPE, they just need to be used where appropriate. And dealing with conc HCl, they are definitely appropriate. So down here where we're dealing with hydrochloric acid, the last section, I just emphasise PPE in general. As I say, that means lab coat, safety glasses, closed shoes, hair tied back, training and general supervision again. Then the risk rating section, I'll go through that in the slides, I think. So, breaking it down again, 3 stages that I was talking about just before. Then looking at the hazards in each stage. So for collect equipment, fairly minor broken glass ones. The much more serious conc HCl ones. So the 3 really bad things that can happen: you can breathe in the fumes, you can get the stuff in your eyes, you can get the stuff on your skin. And then finally dealing with the dilute hydrochloric acid. You don't want to get it in your eye, you certainly don't want to get it in your eye, you don't want to get it on your skin, but it's not going to be as absolutely devastating as the conc. Now when you come to do yours, you're going to need to have information about the substance that you use. And I've tried to find simplified safety data sheets, SDSs, and this is not a particularly fantastic one. It gives some information. So this is for ethanol. There are others in the documents for propanol and another one for butanol and pentanol. And as I say, if you're using another organic molecule, I don't know whether we've got data on esters or not. Esters boiling point volatility is going to be similar to pentanol, so just take the hazards for pentanol if you've got another organic molecule. Now, so for ethanol, it's interesting with ethanol, they're really only talking about the flammability of ethanol. It's a volatile substance, which means produces enough vapour, it's got a reasonably low flash point, so it will sustain combustion at a reasonably low temperature. It's also got an explosive vapour-air mix at that range of percentages. So you've got to keep its concentration down for that reason. What they don't mention with ethanol is its central nervous system effects, which is rather odd. I think it's basically because if they recognise that, they would have to recognise that every solution of ethanol that is sold really should be sold as a substance that is regulated in different ways to the licensing laws, which have every bottle shop, every supermarket selling huge amounts of it. It does have central nervous system effects, so if you breathe in the vapour, it causes drowsiness and dizziness, and it really should be on this list. I'll be disappointed if I don't see that as a hazard. So 2 hazards, the flammability and the drowsiness and dizziness if you breathe in the vapour. If you, obviously, you would never ingest anything in a chemistry room. You can absorb it through your skin as well. So then, once you've identified the hazards due to the equipment and the particular chemicals you're using, you then look at what you're doing to control the risk. And various different controls. PPE, of course, barely needs to be said because, of course, we're always wearing PPE. What is the risk rating? Now, here's where we need to come up with a risk rating based on two things. The consequence, how serious the effects of this particular hazard is going to be, and how likely it is to happen. So cuts due to broken glass. How serious is it? Well, the sorts of things that are likely to happen are going to be pretty minor. You're not going to lose time from school, from work, for a little cut on your finger. You'll get a band-aid, you'll go home, it'll be okay. How likely is this to happen? I don't know, can't remember when the last time I had a cut due to broken glass in my class was. Certainly not in the last year or so. So, probably less than a year. Probably not likely to occur in a year. So most definitely, those two lines make it low risk. The third part, where we're dealing with the dilute acid, again minor, a little bit of eye acid in your eye. You're going to wash your eye out. You're probably not going to lose any time at work. In fact, I probably think that might be moderate, rare for getting it in your eye. Getting it on your skin is going to be minor and unlikely. I don't think I've ever had anyone get anything like that in their eye in my teaching career. So let's keep it that way, okay? And the significant one is, of course, the concentrated acid one, in the second section. Now, it's possible that you're not going to die, but you could get a serious injury if you get conc acid in your eye. However, this is very unlikely to happen. I would still consider it to be a moderate risk, which is why when this prac runs, I'm sort of breathing all over you in the fume hood, making sure you do it right. You don't take any risks. Then if you're doing a sort of more formal risk assessment, you'll have to take the risk ratings and take it one step further. If it's significant or high, you have to take further control measures. You cannot undergo the activity if you don't. If it's moderate, you should think about the further control measures. And for me, that's that extra level of supervision. If it's low, that's okay, you can keep on going. But of course, always work safely. And close supervision, as I say, is the one that the further action needed for the conc acid. So on Google Classroom, I would like you to do the risk assessment in the template that's provided, using information about the chemicals that is attached, and submit it. Environmental considerations, you need to just mention how you are going in your method. You need to mention how you're going to dispose safely of any wastes. If it's a hazardous waste, basically there are two classes that you might come across in most chemical pracs: organic chemical waste, inorganic chemical waste. Organic chemical waste, you put it in an organic waste bottle and we'll pay a company to come and take it away for proper disposal. The inorganic chemical waste will do exactly the same thing, but in a different bottle. So make sure it's clear what type of hazardous waste you are producing, how you are going to get rid of them.